So here's the lecture associated with section 3.4, velocity and other rates of change. Um, One of the things that happens in our particular textbook is that they introduce an idea and then later they name the idea. We came up with this idea that, you have a function and you took 2 points on the function and you get a slope, and we call that a secant line. And we can do the slope of the secant line but we also call this the average rate of change, right? Now, if we use that average rate of change to, let's say, estimate, and again, in this case, I'm going to call that a tangent line, slope. We also call that the instantaneous rate of change. So we've introduced these ideas, but now we're going to give names to them. So an instantaneous rate of change literally is the derivative of some function. Now, we want to think of these as rate of changes because one of the things that calculus is really, really handy for is actually applications, especially in fields like engineering and physics. But let's just talk about the fact that we might apply this idea of an instantaneous rate of change or an average rate of change to functions that are not just f, but rather they represent something. Let's say, for example, find the rate of change of the area of a circle with respect to radius r. Okay, well, what does that look like? I say that I have a function. Okay, that function is a equals pi r squared, for example. That is a function. What might I do to that function? I might take the derivative. In this case, with respect to r, the independent variable of this particular equation. And when I do, I get dA dr, which I might also read as the rate of change in area with respect to radius. And I go ahead and take the derivative of the of this other side, and I get 2 pi r. I bring the power down, multiply by the pi, reduce the power by 1. Great. So we have now found answer A, the rate of change in the area with respect to the radius r. What can we do with it? Well, let's evaluate the rate of change when r is 5. Let's introduce another little bit of notation. The rate of change when r is 5. So we've got this symbol, we've got this vertical line that we pronounce when, and then we have some condition that we're going to impose on the situation when r is 5. And that's going to be 2 pi, and every place we see an r, we replace it with 5. And that's going to be 10 pi. Well, what about the rate of change when r is 10? Well, that's going to be 2 pi times 10, or 20 pi. All right, great. And then that's our answer for part B. If r is measured in inches and area is measured in square inches, what would the appropriate unit be for dA dr? Okay, well, the way we do this in part C is we say dA, A is measured in, this is square inches. dr, or r, is measured in inches. So we would say that the appropriate unit for dA dr would be inches squared per inch. We see 20 pi more inches squared for every additional inch that r got bigger when r is equal to 10. Now, you may be tempted to rewrite this as just inches. You can. I mean, inches squared divided by inches is inches. But I think this gives a better explanation about the kind of thing that we're talking about. how much is this unit, this thing, changing as the independent variable gets bigger by 1 unit. And that's one application of this thing called the derivative. But what if our function gives a position given some time? That position is a function of time. Well, let's bombard you with a bunch of new vocabulary. And that is, how about the first word that we're going to add to your vocabulary? Displacement. Displacement can be thought of as delta x. Now, I'm going to make a distinction right here. When we use delta, we talk about big change. So delta s is a big change. ds, like we see maybe perhaps in the denominator of a derivative, these are really small changes. Small change. Okay, so a big change in the position, a displacement, can be found by taking and finding the position at some time plus some additional extra time, a delta t, and subtracting off the original position. So think of this as a future position. Think of this as a current position. How much did the position change as I went from my initial position to some future position, delta t in the future? Okay, and again, t is time. So delta t is talking about going into the future a little bit. The average velocity of that object is how much displacement is there per how much time has passed. Okay. Oh, if position is measured in meters and time is measured in seconds, then delta s over delta t is meters per second, for example. And we talk about that as being an average velocity or an average rate of change, like we mentioned earlier in this lecture. But we can also call something a instantaneous velocity, and that's going to be just like we used the expression instantaneous earlier in the lecture, meaning that we're going to talk about it as a derivative. Okay, so the velocity is the derivative of position with respect to time. Okay, and you can see here a slight variation on our definition of a derivative. The only thing that's different is that we're talking about changes in time instead of h, and we're talking about the function being a function of time. So instantaneous velocity is the same as the tangent line slope. It's a derivative. Speed and velocity, as you may have encountered in your science classes, are not the same. Velocity can be positive or negative. Speed is the absolute value of velocity. And so you can see speed is the absolute value of velocity or the absolute value of position with respect to time. The third thing we're going to add to this list is acceleration. Acceleration is how fast are the rate of change in velocity with respect to time. So we can think of acceleration as being change in velocity with respect to time, or we can think of it, since velocity is the first derivative of position with respect to time, it is the second derivative of position with respect to time. All right. Please recall that, let's say again, if the units for position are meters and the unit for time is seconds, that a typical unit for this kind of stuff would be something like meters per second for velocity, also meters per second for speed, but for acceleration, because you're already taking the derivative of something that's meters per second, its unit is going to be meters per second squared. All right, let's go ahead and apply these ideas to a problem. There's a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height that is where the height of the rock is a function of time. 160t minus 16t squared after t seconds. How high does the rock go? Okay. Well, I look at this position as a function of time, and I see something parabolic. I might want to know. This is my time axis. This is my position axis. If it's parabolic, I might ask, is it a parabola up or down? Looks like this one opens downward. It looks like I could factor out a 16 and get 10, or factor out a 16t, and I get 10 minus t. Oh, looks to me like it has 0 height at time 0, and it has a second of 0 height at time 10. If I was just using skills from the earlier class, I'd say, oh, there's the parabolic path, or a parabola that describes the height of the rock. And I'd say, gosh, it looks like it reaches its top height at 5. So I might say something like, hey, to answer question A, what is the position at time 5? 160 times 5 minus 16 times 5 squared. Oh, can I do this in my head? 16 times 5 is 80, so it's 800. And then 16 times 25, it's like having $4. So it'd be minus 400, I think. Yep, I think that's right. So I'd say that's going to be 400, and my units, because its position is in feet. Now that's one way to attack the problem using, again, skills and knowledge that we had otherwise. But let's take a look at this problem slightly differently. When that rock changes from going up to going down for a very short amount of time, an instant, let's say, the velocity is 0. Maybe I could take the derivative of position, which is velocity, and get some insights. For example, the derivative of 160t is 160, and the derivative of negative 16t squared is 32t. If I set that equal to 0, I get 160 is equal to 32t. If I divide by 32, lo and behold, I get 5. So using calculus, we can say, oh, I know this phenomenon happens when velocity is 0, and I can use calculus to find that same thing in case we didn't notice that. Or perhaps maybe the position is not a parabola. I mean, we don't have that possibility for other functions. So that concludes part A. What is the velocity and the speed when the rock is 256 feet above the ground on the way up? Okay. So we know that this is 400 feet, it's apex, and then somewhere along here, it's 256 feet on the way up. Okay, well, let me see, when does that happen? When is the position 256 going to happen? Minus 16t squared. That looks like I'm going to have to solve that algebraically. So how about 16t squared minus 160t plus 256? Oh, my handwriting is so sloppy. Is equal to 0. Let's solve that. I'm going to factor 16 out to hopefully make the factorization a little bit easier. Factoring a 16 out of all the terms, t squared, negative 10, and plus 16. So do we have a factorization that works there? T and t. Looks like this is going to be 2 minus signs. So I need 2 numbers that multiply to get to 16, but add to get to 10. How about 2 and 8. That should be a t minus 8 there. Let's see, does that answer make sense? At 2, could that be? Yeah, that looks like it could be a legitimate answer. There should be one answer before the number 5. And 8, yeah, that looks about right. Okay, great. So we found the time in which the rock is 256 feet on the way up. And if I said, hey, what is the position at time 2? 160 times 2 minus 16 times 2 squared. 320 minus 16 times 4. I think it's 64. 200 and, oh, what am I going to say? I don't need to know this. I know it's going to be at a height of 256. That was all a big waste of time. Let's stop that. What is the velocity when we're at that time? Well, again, we've already found that velocity is 160 minus 32. So the velocity at time 2 is 160 minus 32 times 2. That's 160 minus 64. That looks like 96. And units, feet per second. What about on the way down? That would be, what is the value of this velocity at time equal 8? 160 minus 32 times 8. 160 160, 32 times 8. 32 times 8, that's 64 times 4. I think it's 256. And I think that ends up being negative 96 feet per second. Okay, velocities, remember, velocities can be negative. But what about the speed? Here's the notation we'll use for speed. The speed when t is equal to 2 is 96 feet per second. The speed when t is equal to 8 is also 96 feet per second. Yeah, when you ignore friction and all that kind of stuff, you get these nice little things. It's 96 feet per second going up, 96 feet per second going down. What is the acceleration of the rock at any time during the blast? Well, remember, we got velocity by taking the derivative with respect to time of position. We are going to get acceleration by taking the derivative with respect to time of velocity, which in this case is the derivative of, where's my velocity again? Let me highlight it. Velocity, there it is, 160 minus 32, and that gives me an acceleration of 32. And because this problem was given in feet, position is feet and time is in seconds, this would be in feet per second squared. And some of you may recognize that as the gravity constant, at least in the English system. When does the rock hit the ground? Well, we already calculated that. So part D is, we notice that position at time 10 is equal to 0. So rock hits ground when t equals 10. Oh, probably should put in units. Seconds. There we go. All right, let's try this again. See if we get some other insight about this whole process. So as a particle moves along the lines that its position at any given time t, when t is positive, is given by the function, and where s is measured in meters and t is measured in seconds. Find the displacement during the first 2 seconds. Now, what was that formula for displacement again? displacement was the position at a time plus delta t minus a position at some time. Or in this case, our initial position is 0. We're going until you go 2 seconds. So 0 plus 2, delta t is 2. And we're going to subtract that by the position at 0. So what is the position of 2 minus the position at 0? I'm going to do a little side work here. Position at time 2 is 2 squared minus 4 times 2 plus 3. That's 4 minus 8 plus 3. That looks like a -1. And then position at time 0. Oh, that looks like pretty easy. That's 3. Our displacement then is -4 meters. What does that mean? That from time 0 to time 2, the particle moved 4 meters. Particle moved 4 meters. And we're gonna say that positive is moving to the right and negative is moving to the left. So it moves 4 meters to the left. There we go. And that's part A. What is the average velocity during the first 4 seconds? So velocity average, what was that formula? That was position given some time and some change minus position given some time. And this is all divided by delta t. All right. What time are we starting? The first 4 seconds, well, we're starting at time 0. We're moving until we go to 4 seconds. And again, delta t is 4 because we move 4 seconds. I'm going to need to know what is S of 4. That's going to be 4 squared minus 4 times 4 plus 3. 16 minus 16 plus 3. Looks like it's just 3. So how about 3 minus, and 3 over 4. Oh, 0 over 4. The average velocity is 0 meters per second. Well, if you end up in the same place as you started, even though you moved in between there, some of the movement has positive velocity, some of the movement has negative velocity, and it nets out to a 0 average velocity. Now, is that the same as the instantaneous? Well, for the instantaneous, we're going to actually need to find just the plain old velocity, the instantaneous velocity, which we do by taking the derivative with respect to time of the position equation, which is going to give us 2t minus 4. That means the velocity at 4 is 2 times 4 minus 4, 8 minus 4, which is 4. And again, that's also going to be meters per second. So at the instant that we're at time equal 4, particles moving, it's positive velocity, so it's moving to the right. At an instantaneous rate of 4 meters per second. Great. What about the acceleration at time 4? Well, what do we say acceleration is? Gosh, my D's and my A's look very much alike. It's the derivative with respect to time of velocity. Well, velocity we said was 2t minus 4. So that's going to be 2 meters per second squared. And because it's a constant, since there's no t in there, that means the acceleration is always 2 meters per second squared. Okay, and part E, describe the velocity or motion of the particle. For what values of t does it change direction? Okay, let's just remark here. Changes in direction happen when velocity is equal to 0 and velocity changes sign, meaning it goes from positive to negative or negative to positive. If we know that velocity is earlier calculated right here, if we know that velocity is equal to 2t minus 4, we can find out that it changes velocity when t is equal to 2. Now I'm going to do a little number line here to summarize what's going on with velocity. Prior to 2 and after 2. Let's think about, oh, by the way, velocity doesn't exist prior to 0, right? Did we get that in there? Yeah. Time is always positive in this particular instance. So in this range, what kind of values does velocity have? I put in the number 1, the number 1/2, or the number 1.5. All of those values, when I plug them into 2t minus 4, give me negative values, meaning moving to the left. And then what happens when I take numbers that are in this region and plug them into my velocity equation? Numbers like 3 or 4 or 5. I get positive numbers, which means that I was moving to the right. So we could say the particle starts at position, we calculated that there, started at position 3, moved to the left until time equals till time equals 2 seconds. Then moved to the right from then on. There we go. That's a pretty good description of what was going on with the with that particle. All right, and that concludes our 3-4 lecture.